Okay, so right now we are in week 4. So we are in the 31 GC week 4 on the wind turbine operations. Okay, so we have covered some of these materials, but it's important to recap as this session is recorded for our friends in UK. Alright. So in wind turbine, there are two main types. One is the horizontal axis wind turbines. Okay, they are typically larger, so you're expecting power from 500 kilowatts and above. Here it mentioned up to 5,000 kilowatts, but there are larger wind turbines available. So 15 megawatts and 18 megawatts will result in diameters of over 230 meters. Okay, so with this diameter, your rotor will have a radius of half of that, and in this size, 500 to 5,000 kilowatts will probably be in the range of 40 to 120 meters diameter. These three blades, height of 5 to 120 meters, wind speed, depending on the local wind speed, it could be from 3 to 30 meters per second. But this rated wind speed is 12 to 16, and rated rotor speed will be just 12 to 40 RPM. Okay. So a different type is the vertical axis wind turbine. Now, the difference is that they don't have a gearbox and there's no yaw mechanism. You don't need to rotate to face the wind direction because it can accept the wind from all directions. Okay? The wind contribution from all directions will contribute to the speed of rotation. However, the disadvantage of the vertical axis is that the location of the lower part of the rotor is near the ground, where the speed of the wind is actually lower. Alright? And it has a lower to medium efficiency. There's large variation in the aerodynamical power because sometimes there may be clash of the wind, so the output power here may be lower. The maintenance is more difficult and there's a large area required on the ground. Okay? So what are the main components of the wind turbine? So as you can see here, we have the blades. They are connected to the rotor. The rotor is connected to the low speed shaft. The low speed shaft will be then connected to the gearbox, and the gearbox will be connected to the generator, where this will generate the power and then transmit it to the electrical system. On top of that, there is also all the various controls. So you have the pitch system to control the pitch of the blades. You have the yaw drive, the yaw motor to rotate the angle or the direction of the tower to face the direction of the wind. You have the controller on the generator itself to manipulate the voltage or current if necessary. You have the wind vane and anemometer to tell you about the direction of the wind and the speed of the wind. Okay, so overall, when mapped into your block diagram, it will look like something like this. Okay, your blades are here, you have your pitch control, followed by your drivetrain, and then you have your electrical systems where you have your controller. You also have your protection systems and together with the harmonic filters. Over here, the yaw system or yaw control will be governed by the direction of the wind or the yaw motor, so that will link that system together. So overall, we have a supervision and management system to control all of this. So in the wind speed, it consists of both the mean wind speed together with turbulence. And usually the mean wind speed is hourly. It's critical for our energy performance and this waveful distribution. So you get more of the 7 to 8 meters per second rather than the rated speed. And the turbulence is the fluctuations of the wind. So in between the mean wind speed, there will be wind fluctuations. And this would contribute towards the power quality and also wind turbine fatigue, but that one is on the different distribution altogether. So overall, our wind energy is governed by the equation. Half mv square. Okay, and we're going to calculate the power. So this is the rate of change, okay, of the energy, where you have to divide this over time, and when you substitute in all the values, you will get this half rho A B omega Q. Okay. How to get this? Essentially is B omega over time. Okay, so if you expand this equation, you get half m. Okay, m is rho A. What is the volume? Okay, the volume would be the volume of the cylinder. So you have your wind. This is your area plus this. Okay. Rho and B. Rho and B times with V omega square. But this V is the volume. So the volume is in meters, and we have what we call the time, right? So you have the time. So what you can do is you can take out the V over T. Okay, so it's actually equals to the area times with the distance. So it's this is equals to meter per second. So you can just equate it to the wind speed. So lastly you get half rho A wind speed cube. Alright? That's how we got to this. Okay. So rho is the density of air. So rho is the density of air, and then A is the rotor area together with the wind speed, which is the V omega. Okay? And the wind power that is extracted by your turbine will be just a portion of this. So you have a term called CP, which is the coefficient of performance. Okay? Coefficient of performance, and that is governed by the tip speed ratio and also the blade pitch. Okay, these two values. The exact calculation of CP is this equation, but you are not required to memorize this. Okay? If so happen you need to use this equation will be given to you. Alright. So that is on the CP. There is actually a very complex mathematical model to get this equation out, so which you are not required to know. Okay, what you should know is that CP is just coefficient of performance, so this one ranges from 0 to 0.59, which is the theoretical limit. Okay, and it can be seen that if we plot a graph of the tip speed ratio and the different blade pitch angle, it's not so clear here, but blue is 0 and this is going up to 17.5 degrees. Okay, so at 0 and at tip speed ratio of 5, you are getting the highest coefficient of performance. Okay, so as you change the blade pitch angle to the green one, 2.5 degrees, that decreases, but perhaps in the higher tip speed ratio, you will have a higher coefficient of performance there. Okay, so in other areas as well, maybe in this range, a low tip speed ratio, other performing better than the blue. Okay, but most of the ranges, blue is the best one, so you can determine from this. And what does this tip speed ratio indicate? You have the radius and rotor speed over the wind speed. So a high wind speed will indicate what? A low tip speed ratio, right? And then a low tip a low wind speed will indicate this high tip speed ratio. Okay, so you can determine in this manner. And the efficiency of the different types of wind turbine. Just now we saw the two, horizontal axis and the vertical axis. So if we were to plot it in terms of tip speed ratio, as I mentioned, over here represents the over here represents the value for the low wind speed. So a fixed pitch horizontal axis wind turbine could be operating somewhere around here. Okay, whereas a simple H-type vertical axis wind turbine are all in the lower range. Okay, so this is only within the 13%, as we saw here. We only reach a certain portion of it. Okay, so these are the overall efficiencies. We can see the horizontal axis are more or less in the higher range of the efficiency side. Okay, and we have two types of wind turbine will be classified by the speed, okay, which is fixed speed and variable speed. So in the fixed speed, the advantages is that it is simple and low cost. Okay, it's simple to implement and low cost. However, it is not aerodynamically optimal. So the synchronous or induction generator, the generator speed are practically constant at normal conditions, but because of the way it costs, you will select normally the induction generator. It will give you better power quality and lower mechanical stress. Of course, with the fixed speed, you can't adjust the speed that much, so you have no power factor correction. Okay, so for the variable speed, which is the second type, you have better performances and are able to accommodate the low wind. Okay, so it is more costly because of its complexity, but at the end of the day, you get the better energy performance. You have lower mechanical stress. For the permanent magnet synchronous generator, you don't need the gearbox, so that will result in less noise. And you also have the power factor correction, so you have better power quality overall. Lastly, you can provide grid support through the voltage control capability and frequency control capability. Okay, so these are the two types based on the speed. So what is yaw control? Yaw control will be rotating the yaw system around the tower axis. So you can't use this commonly. The reason because it would damage the wind turbine structure. Okay, but you would use this to maximize the output power. Okay, the input wind coming and the output power. So it's limited to small capacity wind turbine due to its mechanical stress. In the offshore, more or less you will know where the wind is coming from. So it's more for the onshore, where oftentimes the wind may be in different directions. Okay. So we have covered this. If we want to control the aerodynamic power, one of the ways is we could look at the tip-speed ratio or the pitch angle. So depending on the wind speed, okay, you have a typical power speed curve here for the maximum power. Okay. So you may adjust your rotor speed to get the better efficiency depending on the wind speed. So this is the power curve. So how to draw the power curve is as follows. You have firstly a value called the cut-in speed, and the second one is the rated wind speed. So from the cut-in speed to the rated wind speed, we are plotting the power. Okay. So cut-in speed is where it's first starting to generate, and rated wind speed is the maximum power that it should generate. So this is where we call the rated power. Rated power. So it's in this exponential because this is in this form, right? V cube. So it will have an exponential growth as the wind speed increases. And once it reaches the rated power, you would then curtail the output to limit it towards the rated power until the cutoff speed. So at both before the cutting speed and after the cutoff speed, the power is zero. Okay, the power is zero. So you have a couple of ways to manage this. At the values that we have set here, one is the active stall control. So there is a way for us to stall the wind turbine. Okay, so you may want to stall it after the rated wind speed. You may be slower than the pitch control, but at least you will get it come down and then get it towards the rated power. So actively means you will have to do a control and then they will adjust accordingly. Another one is the passive stall control, where the blades are designed somewhat to be less aerodynamic at a higher wind speed. Okay, so you don't need to make any adjustment, but it will have a higher drag as the wind speed increases, so it will reduce the power output overall. So in fact, you are actually not getting the rated power at a higher wind speed. So it may not be what you want. Okay, the third one is the pitch control, where we adjust the pitch, okay, according to the wind speed. So if the wind speed is higher, so the pitch will slightly tilt until it reaches the point where it's cut out, so you will stop it entirely. Okay, so the pitch control is actually the best of the three because you're able to track closely the rated power. Alright, and if you are required to plot, you need to be able to differentiate both. This is the powers, the wind power curve, and then the three power strategies. Power control strategies are these: active stall control, pitch control, and passive stall control, which are explained in this slide. Okay, all there. Both questions have come up before. One question on the wind power curve, and then one question on this wind turbine controls. Both have been asked before, but it's usually either or. They will not ask both. Okay, so the typical performance will be when less than cutting, no generation. When after cutout, no generation as well for safety reasons. So in between the cut into the rated is the most optimal extraction of power. You will have high efficiency, but it will drop, when it's closer to the rated speed. Okay, and between rated to cut out is where you try to aerodynamically control it to limit it at the rated power. Okay. Any questions on this so far? No? Okay. So in order to select, the best wind turbine, normally we will consider the following. We will consider about the cost, reliability and maintenance, weight and size, and energy performance optimization together with good power quality and great support capabilities, right? The last one is that we need it to be in a safe operation to avoid mechanical and electrical stress. However, all of this is just for selection of the electrical components. We also need to consider about the power quality and the grid connection, right? How would it minimize the power fluctuations? Will it be able to provide low currents during operations? What else? We want to restrict harmonic distortion, low contribution to fault level, power factor regulation capability, fault control capability, and grid support capability. All of which, if we saw back earlier, is not available in this, the fixed speed. This, all those power quality criteria is only available in the variable speed because it has the you have the ability to vary the speed. Okay, we'll go through that. So there are four types which we consider as the common configuration. Can I erase? I remember in the B30EK, you all have one final SM is the objective style question.
Yeah.
You all like that style? Don't like? Why?
I don't know, I didn't choose that.
Oh, you didn't choose that. I'm considering that.
I like that I can have errors in my answers, but still get points, you know.
No, you just choose the other one, then the last one you just choose all A.
No, when you choose, you all have just write like A, no A, and like B, C, and like what?
Yeah.
Just like this.
Yeah.
Do you all have like the paper or not?
No,
Just normal.
I thought they
normal
Okay.
Yeah, some questions you have to show your working.
Yeah.
Some questions you have to show your working.
Some question to show working.
I mean, I don't know, too.
So it's show working, but you come to the answer.
Because it'll be like extra marks.
Okay. Interesting. I mean, the midst of preparing.
Can you tell which one?
Like it,
Tips. Give tips. God.
Okay, so the first type is the fixed speed wind turbine, or also known as the one of the type is the squirrel cage induction generator. We call it the fixed speed squirrel cage induction generator. So if you were to draw it, basically you have your wind turbine followed by the gearbox. Okay, and the generator. Followed by transformers and so on. Okay, so this is driven by the turbine and your stator is directly connected to the grid. The rotation speed only varies slightly between 1 to 2%, and in some cases you have reactive power compensation through the capacitor bank. Okay. That's the capacitor bank. So you will have compatibility with the grid code requirements for reactive power control, but this only can be achieved with the SVC or STATCOM. This STATCOM and SVC we will cover in a later topic, but what it means is that it's essentially a ancillary product or tool to support your wind turbine. It cannot stand alone without this part. And for the grid code requirements for active power control, this one relies on the pitch or active stall control. Okay. So the next one you have the fixed speed as well, but this is another one, which is the Wound rotor. Wound rotor induction generator. So it's not that common to have a capacitor bank, but it's good to have. So it's more common in the type 2. Okay, so maybe in the first one you will have to consider this. So, but the rotational control or variation is up to 10% over here, and it has a slight improvement of the power quality and slight reduction of the mechanical stress. But overall, the characteristics is same to Type 1 wind turbine. Both of these fall under the fixed speed category based on the speed classification earlier. And these were the two earlier types of wind turbine that we have. Okay, and the more common one that we have now is the Type 3. Type 3 is the variable speed, but it's known as the doubly fed induction generator. Okay, so you have in this case a wound rotor induction generator as well. However, the difference is that you have the rotor connected to the grid via this back-to-back voltage source converter. Okay, this will help control the excitation of your rotor circuit. Okay, so hence your rotor speed is actually decoupled from the grid frequency. So the converter here will be a reduced rating. So if you, let's say your induction generator is 1 megawatt, your converter would just be about 200 to 300 kilowatts. Okay, just a third of the turbine rated power, and the speed variation will be around 30%. Okay? 30% of the synchronous speed. So you have your generator AC-DC converter to provide the top control. I'll show you what this means. You have the gearbox. Then you have your generator. Over here you have your back-to-back. Back-to-back here means AC-DC and DC-AC. Okay? And then back to the grid. Okay, so this is what is called generator side and the grid side. Okay, so when they say generator side AC-DC converter, this one is to provide torque control for your blade. Okay, it can help for your torque control, and the generator side will be for the power factor regulation. Hence, you have reactive power control, voltage control, all enabled through the grid side DC-AC. Okay, it's operate in the active power mode. Alright. So that is for the Type 3. And the Type 4 is the also variable speed. So this one I will call it PMSG. Okay, it's not written here. So usually this is a permanent magnet synchronous generator, but there's also other forms of this Type 4. Okay, so for a permanent magnet synchronous generator, the difference would be there is no gearbox, so it's directly connected to the generator, followed by a back-to-back converter, and then to the grid. Okay, so you have the full range of rotor speed variation. So you have wider reactive power control and voltage control capabilities. And the torque control again is via this DC-DC converter with excitation winding. Okay, so you also have short circuit current contribution from the two converters. Okay. So your rated current or power of this turbine will be same as the generator. It will be much greater than this Type 1, 2, and 3. Alright. Okay, so for the grid interconnection, any questions on this part before we end this Type 1 to Type 4? No questions. Okay. So for the grid interconnection, there are two main types. One is the direct grid connection and the indirect grid connection. So these two will vary in terms of the frequency. But definitely you will need these three. One is the power and conditioning equipment, safety equipment, and the meters and instrumentation. Okay, so regardless of this, you will need this power conditioning equipment to match the voltage, phase, frequency, and the sine wave profile to the grid that you are connecting to. Okay, safety equipment, you need circuit breaker, grounding, and surge protection to protect all the device. More so for your variable speed because you are dealing with power electronics here. So you need to protect your power electronic circuitry. Right. So, but there will be challenges in terms of grid connection. The main two are on the variable supply and the variable load. Okay, variable supply and variable load. So variable supply here means your wind. Okay, it's unpredictable, intermittent. You are not able to get the power that you need in times where maybe you need the supply. Or the loads, it fluctuates. So at a time where maybe you have surplus of wind, but your loads are not as much or they decrease. Okay, so those are the challenges that we are facing onto the grid connection. Okay. What time is it now? 11:45. Go on a bit more. Okay, next we'll move on to the energy power conversion. So this one will calculate on the overall efficiency process of your system. So say you have the few components that we have covered just now, the turbine blade, the gearbox, generator, converter, right? Gearbox, turbine blade, gearbox, generator, and converter. Okay, all of these have a certain efficiency. So given your input power in the turbine is governed by the BATS maximum, so it's only 59.3% maximum efficiency, followed by the gearbox. Gearbox also have efficiency of 0.95 to 0.98, and then the generator, another drop of 5% there, and lastly the converter, which may also be about 4 to 5%. So overall, you will have losses along the way. Okay? In each component, there will be losses. So depending on what the question gives you, you may have to account for these losses altogether.
So, will they state this generator as 0.95?
Yes, we will state. Yeah, it will be stated. If it's not stated, you assume 100%. Okay, you don't go and add on. Okay, because there is this losses here, you go and consider. You must follow the question. Okay. So this is a typical turbine in Green Park, Reading. So it's a 1 turbine, 2 megawatt wind turbine. Homes we know for now, 1063. It's about 6 to 22 RPM for the rotor. 70 meters diameter, 85 meters up height. And overall, in a year, it generates 3.5 gigawatt hour with a 20% usage. So let's do some calculation here. So if this turbine is blown by wind traveling at 12 meters per second, so how much electricity will be generated? This from the simple equation that we have learned. Okay, power equals to half Cp, then rho AV2. Okay. So power equals to half. So we know some of these values, and some of the value we have to assume depending on the question. Okay, this question never gives. So Cp, let's assume 0.5. Okay. And rho is 1.225, so this is a constant of the density of air. Why 0.5? Because the Beck's limit is 0.9, so we just assume slightly lower, 0.5. Okay, what about the A? We have the diameter, right? What can we do with that? So area will be pi r squared. Okay, so in this case, r is diameter over 2 squared. So if our diameter was given at 70, okay, what would be your area? You should get this value. And lastly, your wind speed is 12. You plug all those values in, so you should get your power output to be 2.04 megawatts. Is it correct?
Yeah.
Okay, if you were to use the actual Beck's limit, you should get 2.42. And without any CP, you will get 4.07 megawatts. So everyone gets that? Okay, so if with that 2.04, if you have no gearbox, you can omit that, so it will still be 2.04. The advantage of no gearbox will be that it's quieter and is less options for generator in this case. You only can choose the type 4 if you choose to have no gearbox, right? So after that will be the generator, which will have an efficiency loss, let's assume 0.95, and then the converter loss, which is 0.96. So in total, your output power will be 1.86 megawatts. Okay, if we consider the input power just now, 4.07. Okay, so 1.86 divided by 4.07, you will get efficiency of 45.6%. Okay, 45.6%. So if you have a gearbox, then you will need to consider that as well. So that will reduce your output power to the following, and the efficiency will be dropped to 43 to 44% as well. Okay, so the gearbox will incur some losses there. Okay, what about the, I'm going to cover a bit on the applications. Let me have a short break. Okay, so this is the Blyth Offshore Wind Farm. This is in the east coast of England in Northumberland. And there is 2 wind turbines with the hub height of 58 meters and 66 meters of diameter. So this is also a 2 megawatt rating, and the annual energy output predicted is 10.5 gigawatt hours. the cut-in and cut-out wind speed are as follows. It's an induction generator operating at 50 Hz at 690 volt. After they have generated the power, it will be connected to a transformer. So if you look back at the graph earlier, our connection earlier, there will be a transformer here to step up the voltage, in this case to 11 kV for the grid connection. Okay. So this was constructed in 1992, where 9 300 kilowatt wind turbines were erected along the harbour wall. And in 2002, wind turbines were erected offshore. Okay, so this is the first offshore wind farm that we have. Okay. And from our class last week, we have done some of this calculation. So this is example of your doubly-fed induction generator, where you have the rotor connected to the back-to-back converter. One side is 20 Hz for the rotor side, and another is 50 Hz for the grid side. Okay, so if you have a power generator of 2 megawatts, okay, there may be power losses in the converter, power losses in your gearbox, and so on. Okay, so overall, what is the subsynchronous speed in this case? So if we have your synchronous speed at 1000 RPM based on the number of poles, based on the frequency, you get 1000 RPM, right? If you remember your NS. And your S in this case is NS minus NR. Okay, so your NR here is 20 over 50. So 20 Hz. So your F2 is in the rotor side, right? Essentially, what this means is your NR is NS1 minus S, or you can use NS to open it up. You also can replace as the 60 over P, but F minus F2. Okay. So it's the difference between the 50 Hz and the 20 Hz. So you should get 600 RPM. Okay. So if you were to calculate the slip, which is NS minus NR, so it's 1000 minus 600 over 1000. Okay. So you will get this 0.4. Okay, you also can calculate values such as the torque. So your torque is P equals to T omega. So when we want to calculate the torque, is T equals to P over omega M. So the mechanical torque is actually 2 megawatt, but because there's the 55 kilowatt loss here due to the gearbox, so you have to deduct that. And omega M is the 2 pi F. Okay, it should be 20. I think this should be 20. Okay, you should be using the frequency of the rotor, so it should be 20, and you should get your torque as the result. Okay, there's also the electromagnetic power transferred across the air gap. Okay, you can use the following equations. And the electrical power converted in the rotor, okay, SPG. Later we'll see some other examples of this. Yeah. So overall, actually, all of the values that you can find of the power flow will be as such, and you will get the efficiency for 895 kilowatts over the 2 megawatt will be 45% efficiency. Okay, 45% efficiency. Okay, we'll take a short break on this part here. Next, we will continue with the system control of a wind farm.